Okay, I'd like to discuss a superior equivalence principle, and it's superior to Einstein's equivalence principle. So Einstein's equivalence principle says that someone in a spatially accelerating elevator, and what I mean by that is typically rockets or pulled elevator, so it's accelerating through space, is equivalent to someone in the same elevator at the surface of a planet, massive planet. And if you're inside the elevator, all things, and you can't see anything else, you won't be able to tell the difference, and all the behaviors will be the same. But while this was an amazing discovery or realization at the time, it's not a perfect principle at all. There's obvious inaccuracies with it, or it's not the right word, but it's not a perfect equivalence, okay? There's differences. And it's important to, there may be information or discoveries in those differences. So let's take a look at them. The two big ones are in the spatially accelerating elevator, clocks at the bottom and the top will run at the same speed, okay, because they're both accelerating, assuming they're attached to the elevator. While in the two clocks in the gravitationally accelerating elevator will have slightly different speeds. The higher clock will go at a slightly faster rate than the lower clock. That's because the strength of the escape velocity as you go away from the Earth goes down, and therefore the time dilation goes down. That's the biggest one. Within the Earth, there's a tidal force. So this creates a tidal force, but because your foot is being pulled harder than your head. But we're just going to look at it from a clock perspective, which is what we're really focused on. The other small difference is if you stand up, if you dangle accelerometers all over the floor of the elevator, in the accelerating elevator, spatially accelerating elevator, they'll all point straight down. In the gravitationally accelerating elevator, there'll be a slight inward pull towards the center for accelerometers placed at the edges of the elevator versus one in the center. So this is another thing that you can use to tell the difference between a gravitationally accelerating elevator and a spatially accelerating elevator. Finally, my example, which is a little bit of cheating, but if you have someone else's clock from outside in your spaceship and you're comparing your clock to someone else's clock from a spaceship, you'll see that for this one, the accelerating, well, you'll see a Doppler shift, let's just put it that way, that you wouldn't see here. I don't know if that's a fair comparison. No, but beyond the Doppler shift, as this accelerates through space faster and obtains a faster and faster velocity, the difference between the outside person's clock and your clock will increase, and your clock theoretically should keep going slower and slower and slower relative to the outside person's clock. And now I know some people will say that both are slower, but I don't think that's true. But you will see a difference between the clocks as you accelerate through space, while the difference between the two clocks in a gravitationally accelerating field will remain the same. Okay. Now you may disagree with one of those principles, that last principle in particular, but the first two are well known. So is there another accelerating frame of reference that is superior and does not have these easily detectable artifacts to tell the difference between the two? Well, actually, there is, and we can go over it right now. So this is the superior equivalence principle. Okay. All right. Let's say you have a very heavy asteroid, massive asteroid, and a long tether, and let's do it this way, so it's more intuitive. A long tether, and and then you have the elevator dangling from the tether. The length for this example is going to be a very long, 12,742 kilometers, okay? Is the length of this cable. All right. It's also, but additionally, it's moving in this direction at a speed of 11.2 kilometers per second squared. No, just per second. So now it is swinging around the asteroid at this speed, creating a centrifugal force, or centripetal, whatever you want to call it. A fake force. It's still, you're going to feel you are accelerating. Okay. Now, someone in this elevator, okay, with no windows, will feel the accelerating force going down as they spin around. And given that they're inside the elevator and there's no windows, they won't know what the source of that acceleration is. To calculate the acceleration, the acceleration is calculated. So the acceleration centrifugal is calculated by the velocity squared over r, which is going to be 11,200 meters squared over 12,742 kilometers. So we'll just put it into meters. Anyways, and this comes out to be 9.8. I think it's 9.8 meters per second squared, or it's close to it. You can check my math, which just happens to be the acceleration on Earth. And by the way, this number just happens to be the diameter of Earth, okay? Now, to calculate the time dilation, we just use good old Lorentz, and you're just going to plug this equation in, and it's going to be 1 minus v squared over c squared. And you take this velocity, you put it in there, and you're going to get the exact same time dilation of Earth, okay, that you experience on the surface of Earth, okay? And that's just because the escape velocity at Earth is 11.2 kilometers per second, and that's what your acceleration is going to be. Now, just a little more. Let's say this is 10,000 times the size of the weight of this. If effectively you're going to be spinning around this asteroid, even though there'll be a slight wobble in the center of gravity, is going to be more like here, but it's big enough to keep the center here, but it's small enough that there's no real gravitational effect at this distance from that asteroid. So all the acceleration is just due to the centripetal force. Okay. If we look into this elevator more deeply, if we expand it out, you'll see that the clock up the top and the clock at the bottom, this one is moving is in a slightly smaller circle, and therefore is moving slightly slower, and so therefore its time dilation will be less than this one. So when he goes to do the test to see whether he is in a spatially accelerating elevator or a gravitationally accelerating elevator, this will indicate to him that he's in a gravitationally accelerating elevator. Similarly, the pull is directly down from the center of the elevator, so accelerometers at the edges will point slightly inwards. So that test will also tell him that he's in a gravitationally accelerating elevator. So I would argue, because of these two tests, and he can look up, and then the final test, if he's looking at he has the person's clock here on the planet in his window or in a display, he will see that the difference between this accelerating clock, this clock and his clock, the time dilation differences will be the same. It'll be constant, and this clock will run faster than his clock. So in all three measurement aspects, he will believe that he is in a gravitationally accelerating field, even though he is in a spatially accelerating field. And just, again, keep in mind that the reason why his clock is dilating is not because of the acceleration he feels, but because of the sideways motion and the space passing over him as he rotates around the planet. So it's essentially equivalent to being on a planet, except instead of the space gravitational velocity going down over him in a vertical fashion, which is the model we like to use, it's going over him in a sideways fashion. But that will be undetectable from him, at least for the 3 tests we've defined. Now, so I argue that this is a superior equivalence principle to the Einstein equivalence principle, and that is spinning around a circle is the model we should look at for answers as to what causes time dilation and basically what is space-time. Finally, let's see. I know there's Coriolis effects, so that if he walks forward or backwards, or if he throws something, it'll spin to the left, right. So I know there is a way to detect that this person could detect that he's in a spinning circumstances, but for what you lose, for losing that similarity, you gain back other ones that are somewhat more exciting to me. And so the question is there any spinning analogy that we can come up with that might we can incorporate it into the gravitational space-time model that will yield better results or more understandable results than the currently articulated space-time model, which basically is no model at all. There's no model of what space-time is. It's just math. That's it. Thanks.